Hello, everyone, and welcome to my video on covalent bonding. Throughout this video, what I expect to just briefly go over what covalent bonding is and the core tenets about it, and then kind of go through the types of questions I'm going to expect to see on our quiz and our test for Chapter 5. Um, where we're going to start is just briefly with what covalence is, and to do that, we need to kind of compare it to ionic bonding. Um, So ionic bonding, as we've talked about, is ends up being, for the most part, between a metal and a nonmetal. So here we have sodium, we have chlorine, and what we see happen is that atom one is going to give its electron to atom B, which creates a positive and a negative charge, which then attract one another. We see this donation of electrons. One atom gives its electrons to another atom, which forms the octet rule. If we try to do this with certain elements that are nonmetals, and we see, for example, fluorine, it doesn't work out like this. We're not going to end up giving away electrons and tons of them. We talked a little bit about the energy requirements to add electrons and remove electrons when we talked about ionization energy, and those ionization energies end up stacking way too much energy for us to lose all these electrons here in a feasible manner. So what we do instead is we end up having a donation of electrons. And this is where the term covalent comes from. Co just meaning cooperative, togetherness, and valent meaning valence electrons. So what we end up seeing happening is a sharing of electrons. What we're going to see is this electron and this electron here of this fluorine are going to form a covalent bond. And we're going to represent it using um, something like a line here, and I'll draw it over here just to show it. We have one electron here, and then we have the other valence electrons, like here. And what we end up seeing is these two electrons will form a bond. And what that means is that both of our atoms have access to this electron. This electron ends up over here, and this electron ends up over here. So we see that each one of these atoms gets access to that valence electron. They are shared. And if we look at this atom, it looks like it has 8 valence electrons. If we look at this atom, it looks like it has 8 valence electrons. So one electron is shared from each atom to the other atom. And this is called a covalent bond. What we're going to talk about through this chapter is really just the structure, the basic structure of covalent compounds, which are called molecules. So anything that's more than one atom bonded together is a molecule. And here's what the Lewis structure of fluorine molecule is, um, where we have two atoms that are bonded together, and because it's a covalent bond, it's going to be a molecule. Typically, when we have covalent bondings, we're going to draw them as dashes, like this, these lines. And this line is a covalent bond, and it just represents that sharing of valence electrons. So here's our molecule, here's our chemical formula. Chemical formula just tells me that in this molecule, there's two atoms of fluorine, 1, 2, which we can see. We can have double bonds where we share more than 2 electrons from each atom, and here's how we get O2. We'll show it looks like an equal sign, but it's just two bonds. And then we can have triple bonds here, which we'll see in examples like nitrogen. The one exception that you will always need to know is that hydrogen only has one valence electron, because there is only one valence electron, but just there's the 1s and then there's the 2s. So if hydrogen, if here's our 1s, our second electron would fill up our 1s, and because the 1s is completed and we don't have to go on to the 2s, this was effectively the same as an octet rule. So hydrogen is the one example that it's only going to have two valence electrons to be happy. No matter what, that's just kind of how it works. Some just common molecules. So move myself up here. Um, Every atom has to have valence electrons, unless it's a exception, which I'll talk about. And here's our Lewis structures. These are Lewis structures. We're going to spend a lot of time looking at these, especially once we start getting to chapter 6, where we're going to talk about the three-dimensional structure of this. I've written this on a two-dimensional plane, something like ammonia, but as we're going to see, we're going to make this into a three-dimensional model that better represents what this molecule looks like. Um, and we can see the amount of bonds that there are, the valence electrons left over. These are going to have special names, the ones that are unpaired. So like oxygen here has two unpaired electrons, or pairs of electrons. Um, but we see in all of these molecules that each one of these atoms has the octet rule. It has 8 electrons around it. This nitrogen has one, two. This bond, it has one from nitrogen and one from hydrogen, which makes 2 electrons. This bond would be 5, one from nitrogen and one from the hydrogen, and then our final 7, 8. So this nitrogen has 8 valence electrons, which fills up its octet, which gives it that stability, and that's why that nitrogen is happy. I will get back to this when I show us just so I move myself again as I go through some of the practice problems. But when we're going to start telling if structures are legitimate or not, basically, is this the chemical structure of ammonia? And we're going to see a lot of these different structures. If you ever take even AP Bio, just I know a lot of you are interested in AP Bio, you're going to start seeing a lot of structures. You're going to start to see biochemistry. You're going to start to see structures. And I just want to just to show you this. Here is the Khan Academy of AP Bio right here. The very first thing that starts the year is talking about the chemical structure of water, elements and atoms, like elements of life. This is the very beginning of AP Bio. Carbon, hydrocarbon, functional groups. Some of the stuff that we don't really get to, but you open just any of this stuff up, like here, uh, and you start to see, functional groups. You start to see things like this. You start to see these chemical formulas right here for AP Bio. All right. And that's why this is kind of so important because chemistry is involved in all types of these science. These are all different types of, groups that you start to see. And you need this very first chapter of AP Bio. So, all right. Valence electrons, these are known as resonance structures where you end up with certain molecules can have more than one form. Uh, it does matter where the bond is. When you start getting really into something where you end up with something that looks even like this, and my days are shuddering from remembering. But when you get a ring, and you can have something like this for carbon, you can have two structures, and I'm simplifying this a lot because there are hydrogens here, so I should draw them in. When you have something like this with benzene, as this molecule is known, um, you can end up with more than one structure. And you can end up with double bonds basically placed in different locations. And this does have its ramifications. If you ever take organic chemistry, you will learn a lot about this ring right here. You'll hate this ring right here, but there are ramifications for resonance structures. And what ends up happening is that because we can represent something like this both ways, it turns out that these bonds are kind of somewhere in the middle. We get something like a 1.5 bond, where the electrons are, the electrons that make up this bond here, they kind of move so fast that they go all the way in between. It's like a 1.5 bond. Just some examples: carbonate. I show here benzene, the example I just showed. And that's just something to keep in mind. The exceptions. So on your quiz or on your test, I will be as clear as possible about exceptions. Um, You can have two different types of exceptions. Number one is a electron deficient, which we really start to see with beryllium and boron here. Um, it's a weird mix of a mixture between covalent and ionic bonding, which is why we end up seeing this. Um, and it happens just because they have so few electrons that they can kind of have that one s, and it's okay. They don't need to get to the octet. It's really weird, but that's kind of how it ends up working. It's somewhere in between an ionic and covalent bonding, which we'll talk about in our next chapter as well. And then finally, we have the examples where we have something like xenon or sulfur, and they have an expanded octet, which just means that they can have more than 8 valence electrons. Most of the time, just this happens because of d orbitals that can kind of take electrons, like make it energetically work. Um, but I wouldn't expect you to know that just to be able to identify them. Xenon being the only, noble gas that can go out and do this. And it can form these molecules like this. Um, you can see it with chlorine, for example, in some of these ions. Lots of examples. Just be able to identify it. I will be as clear as possible that this is an exception when we start talking about if the structures are legitimate or not. All right, the naming of our molecules here. I'll get to this explicitly when we get to actual examples of this, but what we need to really just focus on is here's these prefixes, which I will give you on the quiz and the test. I'm not, I don't like, I don't like memorizing these. I don't think that's a worthwhile time to have to memorize these prefixes. Um, but you should really just be familiar with them. Um, you just Our naming is pretty similar to how we did our ionic naming. You took the first element, and then you took the "ide" ending, so oxides, sulfides, etc. And then you just have to add these prefixes. And the only time that you don't have to add the prefix is if the first element only has one. So dihydrogen monoxide, the first number is a 2, so we end up adding di, but the second number is, or the second uh, element has a 1 here, which I've circled. It's invisible, but then we use the mono. So dihydrogen monoxide. Carbon dioxide, we don't need a mono. We don't need mono because it's the first element. So there's a 1 here. So the only time that you need mono is if it's the second element, like in dihydrogen monoxide. And it's really just adding the names in. Don't give me dinitrogen pentaoxygen. If you write pentaoxide, even though that's not English and grammatically correct, that's something that is not on my like priority list because you messed up the English on that. I'm gonna keep the slide up though, just because we're gonna get back to naming. That's the brief just overview of what covalent bonding is. Um, I want to get to some of the examples and just a recap for us. And I want to get to some of the examples with this and just really what am I expecting you to do on the quiz and on the test. So the first thing, and you'll get, different structures like these that I have so gratefully made, not these ones, but I made them in paint. They're beautiful. It's really just to count the number of valence electrons that each atom has. And when I give you one that has multiple versions of the same element, they will all have the same amount of electrons. So don't have to worry about that. And then I just asked, do any violate the octet rule? On your quiz, I'm going to ask this regardless, but then I will tell you it's an exception later because there is a few exceptions that do break the octet rule. And how we count this. Basically, when you have an element, each one of these valence electrons counts as 1. And I can zoom in here just to really show us. Um, each one of these valence electrons counts as 1, and each one of these lines is a covalent bond, which counts as 2 valence electrons because it has 1 electron from one element and 1 electron from the other atom. So let's take our boron here. So our boron, and I'm just going to kind of draw the bears what this thing looks like without anything else. So each one of these lines is 2 valence electrons. 1, 2, 3, 4, 5, and 6. Simple enough. This boron has 6 valence electrons, which does violate the octet rule, but that's one of those exceptions I just talked about. And if we take this fluorine, and I'm just going to isolate the fluorine again. Here's our fluorine. It looks like this. It's got one covalent bond. So we're going to take 1, 2, 3, 4. We have all these pairs of electrons. 7, 8. There are 8 valence electrons here. Simple enough. We see an example down here where we start to get into hydrogens here. So our hydrogen here, because hydrogen, it has 2 valence electrons. I won't tell you this is an exception. You don't mark it as violating the octet rule. Hydrogen is not an exception that I would expect you to like be like, oh, it's you have to know it has 2, and it's normal, and that's just always true with hydrogen. It's the only element that we're really gonna see as an exception. Okay, 1, 2. We see this carbon here has 1, 1, 2, 3, 4, 5, 6, and 7, 8. And our oxygen here also has 1, 2, 3, 4, 5, 6, 7, 8. I'm just going to go through just some of these, but this is kind of what I expect from you. Here's an example just down here with this wonderfully faded, with this fluorine atom right here ends up having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this fluorine has 10 valence electrons, which breaks the octet rule, and this structure, therefore, would be incorrect. Just based off of that alone, because I do not specify that fluorine is an exception, and fluorine will not be an exception. Okay? And I will be very clear with which elements on the quiz and on the test are exceptions. Okay. So we get to something like this. How many valence electrons should there be in each molecule or ion? So in this question, I'm only asking for, does each atom violate the octet rule? So in this molecule here, which is methanol, none of these atoms themselves violate the octet rule. But it's possible that a compound or a structure can not have you violate the octet rule, but still be an incorrect structure. This example, N2, this is not the structure of N2. I showed it way earlier. This is the structure of N2. This is what N2 looks like. And the reason for that is because there's too many valence electrons in this structure right here. Nitrogen does not have that many valence electrons. So what we need to do is see how many valence electrons there should be total. Because remember, you're sharing them, but they still originated with their original element. So this carbon started out with 4, it now has 8, but 4 of them started with carbon. So how do we calculate this? We need to use our periodic table, and you need to know how many valence electrons certain atoms have. And just as a easy review, hydrogen will always have 1, it's in group 1. We're going to get rid of these ones here, like this. And the number that's left over is how many valence electrons there are. So boron is in group 13, so it has 3 valence electrons. Carbon has 4, nitrogen has 5, oxygen has 6, fluorine has 7, and if you really wanted to, because xenon, I talked about it, xenon has 8. And then it just comes down to how many total electrons there are. So if we look at BF3, we saw that boron has 3, each of the fluorines has 7. Alright, 7 times 3 is 21, so 3 plus 21 equals 24. There should be 24 valence electrons throughout the entire molecule. Because we haven't given it any electrons, that's just how many valence electrons those atoms have. You can't just add more valence electrons unless you add a charge to it. So there should be 24 valence electrons. And just as a reminder here, what this 3 means here is that there are 3 atoms of fluorine. 1, 2, 3. So here is our chemical formula. 1 atom of boron, 3 atoms of fluorine. There. Alright, so something like this, for example, N2, we have nitrogen, which has, we go to our periodic table, 5 valence electrons. So we have N5 times 2, because there's 2 atoms of nitrogen, 10 electrons. What I want to just get to down here is these ions. So when you have an ion structure, and I'm going to briefly just draw what this looks like. And this is one of the resonance forms that this sulfide or sulfate ion can have. I do want to just double check here. I know I have this one here. Alright, just making sure I'm not missing any central valence electrons. But here's the thing here, is that this ion here, when we draw an ion, we typically draw it with a brackets around it and say that this entire thing has a -2 charge. So this entire ion has a -2 charge. You might see if you end up Googling that they'll localize the charges, they'll put the charge on one of these oxygen atoms. That's not really something that we're going to get into at this time. But here's our structure for our sulfate ion. It has a -2 charge, and what that basically means is that somewhere along the way, something added 2 electrons to this ion. Because again, electrons are negative, so you have added 2 electrons, charge of -2. Just like if you have an oxygen that normally has 6 valence electrons, and if you take an electron and put it in, your charge is going to be -2. Those electrons came from somewhere. Doesn't matter where, but they came from somewhere. So you have to add those 2 additional electrons to your total count. So our sulfur, right here, group 16, has 6. Our oxygen, also group 16, but there's 4 of them, which gives us 24. And then we have to add the charge, which again is -2, which means we've added 2 electrons. We add these up, we get 32. The opposite logic would occur too. If you had a positive cation, you'd have to remove an electron. So example, NH4 right here would be N, which has 5. H would have 1 times 4. And then our charge, oops, forgot the plus there. Our charge would actually be -1 because you've removed an electron. So you would expect this just to have 8 valence electrons. Just that same logic does apply. So with all of this, there's 2 rules. And what I'm going to have you do on your quiz is step 1, you're going to see, does anything violate the octet rule? Because if this violates the octet rule, there's kind of no point in moving on. But I'm still going to make you move on just to have you do it. But if something does not violate the octet rule, and we need to check, does our structure actually have how many valence electrons it should have? There's kind of 2 rules. Number 1, does everything deal with the, not violate those rules? And step 2, are there as many electrons as there should be given the structure? So what I'm going to have you do is I'll give you a structure like this BF3, and I'm going to have you basically count the total amount of electrons in the entire thing. 1, 2, I'm going to say it, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. There's 24 electrons in this structure. Okay? Back up here, when we calculated this, well, we said that boron had 3, and the fluorines had 7 times 3 equals 21. And we added that up, and there should be 24 valence electrons. There are 24 electrons, so it passes rule 1 because I tell you that boron is an exception, and it passes rule 2 because there are 24 valence electrons and there should be 24 valence electrons. So this would be a correct structure. And what you're going to have to do is tell me, is this or is this not a correct structure? Just more examples. I'm gonna do these 2 examples here. Um, just to show you. So here is our methanol right here. We count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 valence electrons. This one passed rule 1 earlier. It did not violate our octet rule, and our answer to question 2, our second rule. Well, we have carbon is 4, oxygen is 6, and then our for hydrogen is 1, and there's 4 of them. So we end up with 14. And these are the same number, so this matches, and this is good. All right, we move on to this one. Both of these nitrogen atoms have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. This passes rule number 1. However, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 valence electrons in this structure. Nitrogen has 5 times 2 gives us 10. So it does not pass rule 2, which means that this is the incorrect structure. That's why this one is wrong. And our example up here is correct, what this thing should actually look like. And that's what you're going to have to do. And on your quiz, I will also give you a structure and just say, is it correct? And I'm going to tell you, you have to show your work. You have to show me that you counted. You have to show me the correct amount of valence electrons to get full credit. Just writing yes or no will not, I will take off. I will not give you credit if you do not show your work. Resonance structures here, just how to draw them is basically you have to identify what's going to happen is this bond is going to move to here. And you're going to end up with something that looks like this. You have to move around the valence electrons too to make sure that all of them have 8 valence electrons. But now here, we're going to end up like this. And we're just basically changing which one of these oxygen atoms does not have the double bond. Which one has the single bond? So something just like this. And we like to draw these arrows in between them. And in our final one, our double bond's going to, or our single bond is going to go onto this oxygen right here. And we end up with something that looks like this. Don't forget these 2 valence electrons. You really just want to make sure that everything else stays the same, and that all of your electrons have, or all your atoms still have the same amount of electrons as they did. This is an example with the chlorine, where it's the chlorine has a expanded octet. Because this chlorine atom has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This oxygen has 12 valence electrons just on it, just to show you another example of that. It happens a lot with these polyatomic ions. Okay, naming here. Here I will give you the prefixes just like this, and really just our rules. Can I type here? I don't know. No. Because there's only one and it's the first element, we do not need a prefix. We just say sulfur. We use that IDE ending. This becomes chloride. There's 2 of these. We're going to take di, put that here. This would be called sulfur dichloride. All right. Again, it's the same root, sulfur chloride. But instead, we're going to take we're now going to take di and put it here. We call this disulfur, and then our 4 is our tetrachloride. Easy, simple like that. You know, you have an example like here, where you have CO. We're going to take our first element, which is carbon. And we're going to take our second element, which is oxygen, give it that IDE ending to call it an oxide. There is one atom of carbon, so we do not need a prefix, but we need the mono over here, and we're going to write monooxide. We're not going to call it monooxide and have that double O. If you include that double O, if you write it like this, I would not take off because that is an English grammatical thing, and I got more important things to worry about. But here's how we get carbon monoxide, CO, which is that deadly poisonous gas that we all need to have monitors in every single building to identify. So that's just really the only rule, is that if it's the first element that has one, you don't need the name. And you can check the answers, the answer key for the rest of these. Right here, this question here, this is just something that we're going to start to really notice, and this is really, really important if you're taking these, functional groups. If you're learning about biochemistry and you take, something like biochemistry, um, carbon and hydrocarbons, just, structures that look like this, how this looks like, this type of stuff. You're going to see a lot of these kind of structures, and you're going to learn that carbon is always going to have four bonds. When a carbon and atom, yeah, carbon atom is going to be bonded a lot, and it will make sense when you start making your compounds. I mean, even here, carbon's capacity for covalent bonding can form covalent bonds to as much as four other atoms. It's always going to have something like that. Just carbon will always have four bonds, and that's what makes it so versatile. And you can start to see these effects if you take AP Bio, just how important carbon is and why it becomes so important. So that's really just something that I think is important to keep in mind, is for the most part, and this is just stuff that we should know. And again, here's our halogens. Halogens, so they all have 7. Just any one of these that you're going to see. It's not something that you would need to memorize for your quiz, but it's something that should be something that you should pay attention to, because it will really actually help with our next question a lot. Especially the right answer. I had a student that came up to me with an answer that was technically correct, but it didn't really follow these rules here. I would have marked it as correct because it is a challenge type of question, but it's not something that I would it's not the correct form, and there's a reason for that. Something that I think you might learn in AP chemistry class, where you talk about the formal charge, which is just what the charge technically is on an atom, and you want it to be as close to what it should be. But generally, hydrogen is always going to have one bond. That's just always going to be true because it can only have two valence electrons. Carbon, something like CO2 or methane here, is always going to have four bonds, which is what makes it so versatile. We'll have four bonds total. Oxygen here, well, we see oxygen, it's really going to have two bonds most of the time. There are a few examples where this isn't true. Just the biggest one that draws to mind is actually carbon monoxide that looks like this. And this is, 10 valence electrons, 6 from oxygen, 6 from carbon, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 10 valence electrons. So there are rare cases where it's not true, but in general, oxygen wants to have two bonds. There are cases that it's not true, 100%. Here's an example right here, carbon monoxide. But most of the time, oxygen will have two bonds. You'll see it, either connected to something else, like a alcohol group, and you have R's used to represent any other elements. You'll see it double bonded in ketones and aldehydes, carboxylic acids. You'll see a lot of oxygens double bonded, but in general, it's going to have two valence electrons. In general, or two bonds. Same thing with nitrogen here. It's rare to see it with four. It's rare to see it with two. It's possible, but generally it's going to have 3. I would not take off if you have an oxygen that has 3 bonds, like I'll show you in the example below, but that's generally what you're going to see. And any halogen, because fluorine has 7 valence electrons, it's always going to form a bond with something else. I don't know, chlorine here. This is really true for anything that is not an expanded octet. Um, the examples above where you have something like chlorine, this chlorine has 5 bonds, but that's because it's the expanded octet. Unless your chlorine or your fluorine is that central atom that is forming an expanded octet, it's going to have 1 bond to it, just as, to get to the octet. So unless you have those rare exceptions, it's going to have 1 bond. Finally, here's the last type of question here. And I'm actually going to show you the alternative that I was shown that a student had came up to me, which goes by the rules, but because of the rules I just said, would technically still be correct. So here's vinegar, acetic acid, and here's the chemical formula C2H4O2. So I will give you a bare bone structure like this. And what you need to do is follow those 2 rules we talked about, where number 1, all of these elements pass the octet rule, except for hydrogen. There will not be any exceptions in these types of questions. Everything has to be 8 except for hydrogen. Just say that now. Number 2, the structure itself must have the correct number of valence electrons. So, what is that number? Well, carbon has 4 valence electrons, and there's 2 of them, which equals 8. Hydrogen has 1 valence electron, and there's 4 of them, which equals 4. And oxygen has 6 valence electrons, and there's 2 of them, that equals 12. We add this up, and we get 24 valence electrons. So we have to put 24 valence electrons into this structure here. Well, let's start with what we already have. We already have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So in this structure already are 14 valence electrons, which means that we need to insert 10 valence electrons extra into this structure. And we can do that by adding them as dots or as bonds. All right. And I'm going to say, just again, in general, especially the examples that I give you are going to follow the rules here, where they're going to have bonds that look like this, generally. So this oxygen here only has 1 bond. So we're going to actually add here another bond here. All right. So I'm going to keep a running total. We're now at 10. We've now gone to 8 because this is 2 valence electrons. This oxygen has 1, 2 bonds. So this oxygen is good. This carbon now has 1, 2, 3, 4 bonds. So it's good. So we now have 8 valence electrons to kind of fit in somewhere. This carbon has 8 valence electrons. So this carbon's good. All of these hydrogens are good. You can just ignore them. This carbon now has 1, 2, 3, 4, 5, 6, 7, 8. This carbon's good. So all that's left are these oxygens, which have 1, 2, 3, 4, 5, 6, 7, 8. This oxygen has 4, 5, 6, 7, 8. And we should get our correct structure like this. Which if we draw it without all of this, which I'm just going to delete all of this now, you would end up just looking like this. And this is the bluish structure for acetic acid. It's a little bit of trial and error sometimes. This is a type of question that it's a challenge question. I completely understand that. If you can tell me how many valence electrons there are and really just try your best at it, you can get some partial credit with this. It's not an all or nothing type of question. Here's the example that a student had shown me that is technically not incorrect, but it's the same idea. But this oxygen has 3 bonds, and this oxygen has 1 bond, which is why this would be mostly incorrect. I would have accepted this because I didn't talk about formal charge. I did not talk about that and that definition to help us, but this would technically be this is not the correct structure of vinegar. I would accept this because it does follow both of these rules, but this oxygen has three bonds, this oxygen has one bond, and unless you really have to, you want the oxygen here to have two bonds. You want the oxygen to have two bonds. So this is kind of what I'm expecting from you for this quiz. I'll ask similar types of questions on the test. Um, you're gonna get one of these on the quiz. It's really the same structure. I think I structured a little bit more clear on the quiz. I'm gonna have you. I'll give you a structure and say, is this the correct structure or not? Um, just without going through those rules. So you need to know those two rules. And I give you the two rules, like I will give you those rules, but you need to know how to apply them and kind of what they mean. Um, all right, so that's all for me for this. This is your kind of deep dive into covalent bonding and just talking about Lewis structures and how we can tell if they are correct or not. We will continue with molecular structures. That's all about chapter 6. We'll get into a lot more. We'll get into the three-dimensional shapes of them, but this is just telling us what they actually look like.